if you see this little guy up here, see it? That means it's recording. So you don't have to ask me 20 times during the class, okay? So it's recording right there. Okay, so I think that we left off last time right here. Yeah, didn't we? Talking about whether you regulate the ECF or the ICF. Yeah, that's where we were. So we were about to do negative feedback. Okay, so now we're going to switch gears just a little bit. It's not going to be dramatically different than stuff you've done before. But what today is really about is sort of giving you the big picture framework of what you are going to guess in physiology. I think it's really phenomenal skill to be able to have a good hypothesis of what you think is going to happen next, and then you can just confirm or revise your knowledge so that you have a better prediction the next time. So that's really what today is going to be about. So how do you maintain homeostasis? And homeostasis is really the whole unifying theme of physiology. It is the thing that you are going to use to figure out what the hell is going to happen next, okay? If I'm bleeding and my blood pressure is dropping, what do I predict is going to happen next? And then eventually you find specific mechanisms by which you can confirm that that's what's going to occur. So homeostasis is, of course, the maintenance of a relatively constant internal environment, right? And that's how we are going to maintain us as a functional human instead of an entropic blob, right? So the mechanism by which you accomplish that is called negative feedback. And so with the concept of negative feedback, what we are going to do, the purpose of negative feedback is when a variable gets out of a homeostatic ideal range, we are going to try to replace it to that range. And so we'll talk about the mechanisms by which you do that in just a second. But first, let's talk about negative feedback as a concept. First, in order to understand what negative feedback is all about, purpose is to maintain homeostasis. And I need you to dump your prior associations with the word negative, right? Because in this particular instance, negative definitely does not mean bad, right? It's definitely not bad, if there was a judgment, to maintain homeostasis, right? And it also doesn't mean lower, because in order to maintain homeostasis, if my blood pressure dropped, what should I do? I should raise it, right? But if my blood pressure went too high, I should bring it back down. So the negative in this instance doesn't even tell you which direction you're going. What it tells you is that I am going to oppose or negate the change, right? So whatever direction the variable was changing in, I am going to act in opposition to that, right? So it doesn't mean lower and it doesn't mean bad. Okay, so negative means that a deviation from the normal is resisted or negated, and the value is going to be returned to normal. Eventually today we're going to talk about whether you're trying to return it to a normal point or whether you're trying to return it to a normal range. And so we are going to talk about several examples of that. But before we get to that, let's just talk about an example of a graph of what negative feedback would look like over time. You guys this week in lab are going to be doing homeostasis and negative feedback and graphing. And with graphing in physiology, there's a really, really common mechanism of doing physiology graphing. And that is basically looking at a variable over time and measuring the variable over time. Okay, and before we go any further, there's a correct way to do these graphs and there's an incorrect way to do these graphs. The independent variable that you're actually not trying to assess will go on the x-axis. The dependent variable that you are trying to assess will go on the y-axis. And if you flip the axes, you're actually saying something incorrect, because this says that the variable varies over time, and let's say we're talking about body temperature. Is that true? Is your body temperature going to vary over time? If you flip the axes, you would be saying that time varies with your body temperature, which is not true unless you're a superhero that I don't know about, right? And you like change your body temperature and go backwards and forwards. It wouldn't be an uncool skill. It'd be a little hard to regulate. Okay, so let's talk about varying body temperature over time. You have been a human. You know that your body temperature is going to vary over the course of, let's say, a 24-hour day. Okay, so let's just like make up what body temperature is going to do. It's going to be a great day in which you get everything done that you meant to get done, and watch how your body temperature varies. So what we're going to do is we're going to get up in the morning. Let's say we get up at 6:30 a.m. And what do you predict about your body temperature when you are about to wake up? It's relatively low, exactly. So your body temperature is going to be relatively low. And then as you get up and start wiggling around, your body temperature is going to raise, right? Your metabolism is linked to your action, but not dependent on your action. And then you're going to have some breakfast, which will increase your body temperature both during and a little bit after, okay? And then this is going to be a good day, right? You're going to be one of those good days where you work out before your day starts. It never happens with me. So you're going to work out, right? After breakfast, you're going to work out. And then you're going to get in your car and you're going to drive 30 minutes to work, right? And your body temperature is going to drop a little bit. And then you're going to work. And if you're anything like me, my body temperature goes up quite a bit when I'm teaching. I get all spazzy and doing that. Okay, so your body temperature is going to do that however long you're working. Okay, and then you are going to drive back home, right? You're going to have some dinner. You're going to watch HBO with your significant other for entirely too long. Then it's a good day, remember? You're going to have sex. It's going to be good sex, not particularly long, though.
It's fine. It's very efficient. Okay.
You got shit to do. And then you're going to go back to sleep, and eventually your body temperature is going to drop. Good? Okay, so what you can glean from this is, there's some information that you can glean from this. Variability is kind of the rule, right? But isn't it, although it sounds like an oxymoron, isn't it predictable variability? So at any point in the course of a normal day, is your body temperature probably going to go up to 104 degrees, even when you're working out on a good day, right? It's not going to go down to 72 either. So if you look and you have enough data points, and 24 hours is fine, but 48 is better, and 72 is better, and a whole month is really awesome for getting data points, what you're going to start to see is that apparently what I'm trying to do is to oscillate in and out of an ideal range, right? So it's not that I never go out of the range, it's that I never stay out of the range if I'm healthy. Does that make sense? So it's absolutely normal for your blood pressure to go up pretty high when you're working out, but is it normal for it to stay high when you're done? No, okay? Is it normal for your body temperature to go up? Yeah, but it's also normal to bring it back in, right? So what you can see is what you're doing is trying to maintain this variable within a healthy range over a long period of time. And conceptually, I want you to understand that it is also normal to go out of the range. What defines disease? Staying out of the range in a consistent manner. So this is not blood pressure, but let's just talk about blood pressure. So if I go into the doctor and my blood pressure is 180 over 120, am I going to be diagnosed with hypertension? No, because what if I ran up the stairs? Right? Does that make sense? So what you need to know is you need to know how it's varying and whether it's varying consistently in the same direction, and that can get you a better idea of what's going on. So you always go out of range, right? Okay, so graphs of negative feedback tend to oscillate in and out of what looks like a normal range. How do you get an idea of the range? Well, since your body doesn't actually speak temperature and it's not going to tell you numbers, you start basically tracking data over a decent period of time. And with enough data, you'll get a great idea of the range. And you'll also get a good idea of what the mean body temperature is, right? And so if this were my example, you'd get a good idea of my mean body temperature, which is just your average body temperature over time. So negative feedback tends to do this over time, and you are going to see example after example after example of negative feedback. I mean, you can do them even with non-human examples. So if you're looking at this particular situation, when you get outside of the ideal and you start to see it go back up to the ideal, you can see, okay, this is an example of negative feedback. I'm not actually getting where I need to go. And we'll talk about how that happens. The way that it happens is what we call a reflex arc. And a reflex arc says that in order for this to occur in the human body, you have to have some physical structures that are actually measuring, responding, making changes, and knowing when enough is enough. So they're actually physical structures that are going to do this. They're not the same structures for all variables. For instance, you don't increase temperature and increase blood pressure with the same physical structures. Does that make sense? So what we are going to get is this concept of what we call a reflex arc. And a reflex arc, let's do the temperature example in your own home before we do the temperature example in your body. So I want you to think about the components, the physical things in your own home which allow you to keep your house at 72 degrees, okay? She's like, 72? Oh, I love 72. Yeah, 68 when I'm sleeping. It's okay, I drive a hybrid car, I recycle. I'm going to keep my freaking air conditioner that way. Okay, so what happens is, okay, let's say you got some kids. If you got some kids, you know they leave the damn door open, right? Okay, because they do. They're going to leave the damn door open, and then your house is going to go from 72 to not 73, but 78, right? And so what's going to happen is I have to have a mechanism of instituting this change. And the first thing that I need is the thing to be measured. So what variable am I looking at here? I'm looking at temperature, right? But then I need a measurer. And in this particular metaphor, the measurer is the thermometer part of your thermostat that measures the variable but doesn't actually change the variable, right? And so it can tell the difference between 72 and 78. And then I still haven't fixed the problem, right? I've just measured the problem. So now what I'm going to need to do is to send that information via what we call an afferent or input pathway, usually the nervous system, right? So I measured it. I need to send it to the place that knows what it should be, right? There is a place that is actually storing your ideal temperature, and it's actually the thermostat part, right? The part where you actually set it at 72. And so you send it to what we call the integration center or the integrating center. And the integrating center is what knows what the temperature should be and how much variability from that, how much error around that is okay. Okay, so there is obviously an error factored in there because does your air conditioner turn on when it goes from 72 to 72.4? No. So you've got it set at a number, but you have an acceptable range of error around that number, which you didn't really determine, but it's in there, right? But we're pretty sure that 78 is going to be too hot compared to 72, right? So it says, measures, sends it in, and the thermostat says hot to how hot? Too damn hot, okay? And then after it's decided that it's too damn hot, it needs to do the other pathway, which is the output pathway. The pathway, the efferent pathway, to the parts that can fix it, right? The parts that can adjust the variable. And in your home, of course, what is the part that can adjust this variable? It's the air conditioner, right? Or the swamp cooler, or whatever the hell you have. So you send it out, okay? And those are called the effectors, the things that can effect the change that you want, okay? But this has to be an arc. It has to be a circle. Because if I just turn on the AC and I never feed the new data back into the system, then I'm going to end up with the opposite problem, right? So do you see why it's a reflex arc? So I dropped the temperature and I have to feed that new information back into the system. And as soon as it is no longer in the error range, then you actually turn off the effectors, right? That makes sense? And that's the same thing that's happening here. Okay, so now let's put the example into the human body. So what are the parts of the reflex arc in the human body for temperature? You may or may not know. So if my body temperature is getting hot, right? So the first thing that you have to do is you have to have places that can measure it, right? So we've got the variable, which is body temperature. The places that can measure it are sensory receptors for temperature. You have them all over the body. You've got them in your blood vessels. You've got them in your skin. You've got them all kinds of places. You've got some really tweaky ones in your brain because your brain gets super pissed off if it gets hot. So these are the most sensitive ones. So let's say the body temperature starts raising and it's actually sending the information via the afferent pathway, which in this instance is the nervous system, to the place in your body that has your ideal body temperature stored. Anybody know where that is? It is the hypothalamus. Yeah, the hypothalamus has your ideal body temperature stored. And so what happens is you send that information to the hypothalamus, and the hypothalamus, the integrating center, actually says, hot. How hot? Too damn hot, right? If you're at 104, it's too damn hot, right? So it's actually sort of measuring and discovering whether the air is acceptable, because you don't start sweating every time your body temperature raises a degree, but you will start sweating at 104, right? So you also start frying at 104. So now the hypothalamus has decided that it's too damn hot. Now you have to do the other part, which is the output pathway. So I'm going to send a signal to the places in the body that can help with that. Anybody have any idea what that is? How can you drop your body temperature? You're going to be sending via the output pathway to the effectors that can affect the change that you want. What? Sweat glands, yeah? What else? Vasodilating to the surface, right? And that will help cool down the body. And then although it's a little more complicated to think of, you can also send it back to your brain to tell you to sit the hell down, go to a cool room, right? All of that kind of sort of conscious. It's a little more complicated example, but still, almost any means necessary to accomplish what you need to do. So then, let's say you cooled your body down. Again, you have to feed that back into the system, or else you're going to continue to drop your body temperature, right? So it has to be an arc that goes all the way around. Now, interestingly and conceptually, this is super duper expensive because there are parts of the reflex arc that you can never stop doing. A lot of times, like right now, my body temperature is probably just fine. Actually, I'm kind of cold in here, but my body temperature is just fine, so I don't need to activate the effectors, right? But do you think I ever want to turn off the sensory receptors or the afferent pathway or the integrating center? No. So do you think I only measure my body temperature like every half an hour? No, because a hell of a lot can happen in half an hour. You can fry your freaking brain in half an hour. So although you might not always need to do the last part, right? The efferent pathway, the effector organ, and a new response, you always have to do the beginning part, right? You always have to sort of check it. So can you start to see why, like, you spend 60% on homeostasis? Because you always have to be monitoring, right? Constantly. You can't just monitor a variable that could kill you intermittently, right? So you're going to always be doing the first part because the integrating center always needs to assess whether a change needs to be made and not just infrequently, right? So you can start to get an appreciation as to why it's so freaking expensive. Okay, so this is a reflex arc. Now to put these terms together, so we've got reflex arcs, we've got negative feedback, and we've got homeostasis. Here's the relationship between them. The reflex arc are the components of the body that maintain homeostasis by negative feedback. Does that make sense? Do you see the relationship between them? Okay. So the whole objective is homeostasis, right? And you accomplish homeostasis by doing this with those parts. Is that okay? Do you see how doing this regularly can result in a graph that looks like this, right? It starts to go up, you bring it back down. As soon as it gets low enough, you know it's low enough, so you turn off those effectors, and then it starts going back up, right? So these things are all related to one another. They're all three basically mechanisms of talking about the same thing. Okay, so now let's talk about something that's related to negative feedback, and it sounds like it's the opposite, but it's totally not. Go ahead. And in the temperature example, the hypothalamus is the integrating center or the integration center.
So then what's the sensory receptor?
The sensory receptor are your temperature receptors in your skin, your blood, your brain. Does that make sense? Now, notice that the example, that's just for temperature.
Yeah.
It's going to be different for blood pressure, and it's going to be different for blood glucose. But we all have reflex arcs, and the parts may change, but they've all got the same components, right? That makes sense? Okay, so now let's talk about feed-forward mechanisms. It sounds like it's the opposite of negative feedback, but it's totally not. What a feed-forward mechanism is if you are one of those people who's very, very regular, you get up at the same time every day, and you go, you eat at the same time every day, and you go to sleep at the same time every day. All of that sort of consistent input is going to give your body a good predictive capacity for what's going to be necessary. So if you get up at 6:30 a.m. every morning and you forget to set your alarm, what's going to happen? You're going to wake up at 6:30 because that's what you've sort of trained yourself to do. Because what your body says is, I think I know how to help you with this. I know that you're going to need your metabolism to raise because you've got shit to do, like within the next 5 minutes, right? So what's going to happen is you're going to be asleep. The alarm didn't raise, but your metabolism starts going up anyway, which wakes you up, right? And if you go to sleep at 11:30 every night, if you're going to try to pull an all-nighter and try to pretend to be 22 again, no. Unless there are chemicals involved, you're going to fall asleep at 11:45 max, right? So what this is called is a feed-forward mechanism. It's your body doing what we call anticipatory homeostasis. It says, I think I know what you're going to need. If it's right about 80% of the time, can you see that it's actually pretty cost-effective to do that, right? That makes sense? So instead of me, I have really irregular sleep patterns because my son is a morning person and my husband is a total night owl, and I really like both of them. So I'm trying to accomplish both things every day, which means I get no regular sleep whatsoever. So if I don't set my alarm, I'm never going to wake up. I have to set 3 alarms just to make sure I make it to the 8:30 class, which is right before this. I hate it. So I will never wake up. It's not going to happen. I will sleep until maybe 4. I don't know. Anticipatory homeostasis uses very regular body patterns to predict what's necessary, and if it's right a lot of the time, then it tends to be a cost-saving move, an ATP-saving move. There are a couple of other examples of anticipatory homeostasis. One of them is if I put food in my mouth, okay, but I haven't actually absorbed any glucose, the food in my mouth says, you're going to need some insulin in just a minute, and it will actually cause your digestive system to release these pro-insulin factors. It's not insulin itself, that gets you ready for what you're going to need. Or there's a simpler one. If you walk into grandma's house and you smell chocolate chip cookies, what's your mouth going to do? It's going to salivate. You're going to start to release salivary amylase to start to break down carbohydrates, because that's what you usually do when you smell chocolate chip cookies, right? And grandma slaps your hand and tells you it's for Relief Society, right? And you're getting damn cookies. That happens every single time. The salivation response will eventually not be as dramatic, okay? She owes you a cookie because she just burned some ATP, and you need to tell her that. You owe me a cookie, Grandma. Or with human sexuality, if your wife sleeps with you on a regular basis and she comes into the room wearing lingerie, you're going to have an anticipatory homeostasis response, right? You could be wrong because she could just be trying it on, and don't tell her she owes you a cookie. Ask her if she will give you a cookie in the near future, please. Okay? So those are feed-forward mechanisms, and the idea is just getting a jump on homeostasis, making a prediction. And when your predictions are good, most of the time it tends to be cost-saving. When they're really not good, you just give up on them. You're not going to do them any longer. Okay, so that's a feed-forward mechanism. And now let's talk about some specific instances of negative feedback, because negative feedback is trying to accomplish homeostasis, and it's going to do it by a reflex arc. But there are long reflex arcs, and there are short ones. There are local reflex arcs, and there are global reflex arcs that go further. So I'm going to give you 2 descriptions, and then I want you to match them to the words just based on your knowledge of vocabulary. So there is the type of a reflex arc in which I have a disturbance in a body system, and I am able to handle it within the system, right? The system has the capacity to handle the change. And then there's a disturbance in the body system in which I am unable to handle it myself, and I have to call a friend, okay? And here's the terminology. There's intrinsic regulation and there is extrinsic regulation. Which one of those terms refers to regulating in-house? Intrinsic. and extrinsic is calling a friend, okay? So we're going to look at examples of each one of these. A good metaphor for this is if somebody breaks into my house, I'm going to call the cops, right? But if somebody breaks into Tony Soprano's house, does he call the cops? No, he does not. It's all regulated in-house, right? He can do that. Okay, so let's look at a couple of call a friend situations. Extrinsic regulation is usually long distance. I have a body system disturbance, but I can't manage it with that body system, so I have to call on another one. The most common friends to help are the nervous system and the endocrine system. They're really common helpers for other body systems. So the objective here is going to be to maintain homeostasis. So here's an example. It's going to be Halloween pretty soon. And if you had siblings when you were little and you got 6 Butterfingers, how many Butterfingers did you eat? I ate 6 because my older brother was a beast. And he's 6'6", and I had to be meaner than him to win. So I had to store my Butterfingers in my guts. That was the safest place to do it. So obviously this is going to cause a disturbance of a variable, probably many, but let's look at glucose. Okay, so what it's going to do is it's going to blast my glucose level through the roof. But I'm not diabetic, so I actually am able to handle that, although I'm not able to handle it with the system that created the problem. So the digestive system created the problem, right? But I can't poop it out fast enough to drop my blood glucose, right? And I could puke it up, but you know, as a kid, there's no way in hell I was giving up those Butterfingers. So now I need to call a friend, and the friend that I am going to call on to help regulate my blood glucose level is the endocrine system. So what the endocrine system is going to do is it is going to detect the high levels of blood glucose. And so in this particular instance, although you may or may not know this yet, the pancreas both has the receptors, the sensory receptors to determine the change. It also has the integration center. Okay, so it's got the integration center in there, and it says, whoa, that is way too much glucose. And so it does what it can do, and it releases insulin into the bloodstream. And insulin does what to blood glucose? It drops blood glucose. The primary mechanism by which it drops blood glucose is that it allows your cells to take the glucose in instead of leaving it in the extracellular fluid. Okay, so your blood glucose was high, your pancreas says, I can help you. Releases insulin, you drop your blood glucose. Of course, what has to happen now to the new level of glucose? Has to feed back to where?
Pancreas.
Feed back to the pancreas. The pancreas assesses it again, says it's in an okay range, and stops releasing blood glucose. That makes sense? So 2 questions. Do you see that this is an example of negative feedback? Yeah, so you can sort of picture it in your head. And the second example, somebody tell me why it's an example of extrinsic regulation.
Because the digestive system caused the problem and the endocrine solved.
Exactly, good. And you will see endocrine system swoop in like a superhero and the nervous system all the time. Okay, but I'm going to do the opposite example simply because I don't want you guys to get into the habit of thinking that negative feedback always brings things down. Okay, so let's look at the opposite example, fasting. This is a digestive system disturbance because either I'm starving or I've heard that people fast here in Utah every once in a while on Sundays. I'm not from around here. Or I've got a doctor's appointment, right? And they say that I have to fast, and my doctor's appointment was supposed to be at 9, and they make me wait in the waiting room till 11, and then I'm going to eat then. So you're fasting. Regardless, it's going to cause a disturbance of blood glucose, right? But in the other direction, right? Your blood glucose is entirely too low. And either you can't or you won't fix it with the digestive system, right? You're just not going to eat with the digestive system. But low blood glucose is unacceptable. Your brain depends on blood glucose. So what's going to happen again is I'm going to call a friend, and it's still going to be the pancreas that's going to be measuring. It's going to be the integrating center, but there's going to be a different back end. You can't use the same effector mechanism because, so the pancreas is going to measure the blood glucose, and it's going to say too damn low, right? And now it's going to say, I will help you with this, but it's definitely not going to release insulin because that would not help, right? It's going to release a different hormone called glucagon. And glucagon is easy to remember because you need it when your glucose is gone. And glucagon is going to go to the places in your body that you store glucose when times are rich, right? After those 6 Butterfingers, I promise I stored some here. So it's going to go to the sites at which you store glycogen. What's the primary location? Liver, Muscles store glycogen for themselves, liver stores glycogen for the body. But, so it's going to go to the liver, and the liver has glycogen, which is stored glucose. And all you do is say dump some of that into the bloodstream. And then the blood glucose level comes up, right? And then what do you have to do to complete the circuit? Feed it back to the pancreas, assess it again, figure out when to stop releasing glucagon. Does that make sense? So same question. You can see that this is negative feedback, correct? And you can see that it is extrinsic, right? Because it's using hormones. Now, there are lots of examples using the nervous system, but they usually don't quite make as much sense at the beginning of the semester, so I'll like save them for a little bit later, and then we'll see them all semester long. Okay? Okay, so let's talk about intrinsic regulation. Intrinsic regulation is when you have a problem in a body system or a tissue and you are able to manage it in-house. It's usually shorter distance, it's usually faster. It's also not usually as robust, meaning it's not able to make as massive changes as extrinsic regulation. So the activities of the cells, the tissues, the organs, or the organ system will change locally and automatically to maintain homeostasis. So here's an easy one. So let's say I've got one tissue or organ that is having a really high metabolic rate, and so it needs a lot of oxygen, but the rest of you is doing nothing, okay? You're just sitting on the damn couch, but your liver is working really hard. Like, for instance, you went on a bender last night and you did 6 tequila shots. What's your body going to be doing the next day? Not a damn thing. What's your liver going to be doing? Oh, crap. Like, trying to keep up. Or you could do it the unfun way, and you could take 6 acetaminophen the day before, okay? Don't do that. And don't take acetaminophen when you're drinking, guys, because they're both detoxified by the liver, and you kill yourself that way. So, ibuprofen. Okay, so regardless, the next day, the rest of your body doesn't need increased blood flow, but your liver does because of the metabolic requirements. So, what does the liver do? It has low levels of oxygen and needs more. So what happens is the liver cells themselves release some chemicals called paracrine factors, which will cause local vasodilation, specifically in arterioles. And will that solve the problem? Local arterial dilation, right, will increase blood flow and therefore oxygen flow to the tissue. As soon as it gets high enough, you stop releasing the chemicals, and then you will eventually vasoconstrict back to normal levels. Does that make sense? So you can see that that is negative feedback, right? Right? It was too low and you brought it back up. You can also see that it's intrinsic as opposed to extrinsic. Okay. And then the next intrinsic example is complicated. The only reason I'm bringing it up to you now is because we'll see it all semester long, and it's really good if you like start getting used to the idea. So this one is regulation of acid-base balance via the respiratory system. Okay, so we just talked about the fact that, of course, when the metabolic rate of anything goes up, it's going to use more oxygen. You also should remember from 1610 that when the metabolic rate of anything goes up, it will generate more carbon dioxide. Yes? Yeah? Sounds familiar? Cellular respiration. If you never learned cellular respiration in 1610, you will regret that in physiology. You will learn it in phys. Okay, so like that pen. So I'm going to show you the relationship that you've got here. Where the hell did it go? Oh, there it is. Okay. So as carbon dioxide tends to go up, increasing metabolic rate, here's what's going to happen. Carbon dioxide will combine with the ever-present ubiquitous water because it's just always around, right? And then it's going to generate carbonic acid, which is H2CO3, which is carbonic acid. And carbonic acid does what acids do, which is they lose a hydrogen ion, right? So they're going to lose a hydrogen ion and generate HCO3 minus, which is the bicarbonate ion. Okay, so before we go any further, I want you to see this relationship. As carbon dioxide goes up, what tends to happen to H+? It goes up. And then what's going to happen to pH? It's going to go down. So this is the relationship that's going to be important to you all semester long. Increasing carbon dioxide tends to lead to an increase in H+, which tends to lead to a decrease in pH. Who cares whether it's a decrease in pH? Changing your pH will change the structure, the shape of your proteins. If you change the shape of an enzyme, you change its functionality. If you change the shape of a receptor, you change its functionality. Same thing with hormone. So the pH in our body is very, very tightly constrained. In your blood, it's 7.35 to 7.45. That's all you get as far as variation. So there's a mechanism that allows you to take care of this. So basically what I have is a disturbance in gas content, which will result in a disturbance in pH content. There is an automatic mechanism that the respiratory system helps with this. And that is, as soon as the respiratory system starts to detect an increase in H+ concentration, it automatically increases your respiratory rate. And so what will that do? Drop your carbon dioxide, therefore drop your H+, and do what to your pH? Bring it back up. Exactly. That makes sense? Okay. And I didn't have to tell the nervous system about it, and I didn't have to tell the endocrine system about it. Is that okay? Okay. So this equation you will see all semester long. All semester long. And this is a good thing to know early, because it'll just sort of help make a bunch of different examples make sense to you. Okay, so now this one, I agree if you think, oh, it doesn't quite look as local because like you generated the carbon dioxide with a cell that wasn't necessarily the respiratory system and then you handled it with the respiratory system, but it didn't actually have to use an intermediary. It actually just responded to a change automatically with a change in the body system that could help with it. So it didn't use the endocrine system or the nervous system. Okay, so some of you guys are not comfortable with pH because people never are because it's got math and it's like a counterintuitive because pH is the negative inverse log of the concentration of hydrogen ions and everybody's like, oh my God, shut up. So if you need practice, interactive physiology has some practice on pH for you. Again, I don't test out of that, but if you want to make yourself comfortable, feel good about that kind of stuff. Okay, so are most organs and organ systems, do they mostly use intrinsic control or extrinsic control? Yes, they use both. And generally what they're going to do is try the cheapest, fastest way first, and if it is inadequate, then they will call a friend. So if your oxygen level dropped in a tissue, what would you try first? Yeah, vasodilation, intrinsic. If that failed, then you tell the nervous system about it and increase your heart rate and respiratory system, right? Okay, so almost every body system has the capacity to do both, and you're almost always going to try the cheapest one first, and that's generally just what the body does, right? So if you were laying sick on the couch, have you ever felt your heart rate go up because you were sick, right? So it totally can happen. Obviously, your heart rate's not going up because you're exercising. It's going up because a single body system is unable to deliver whatever it needs, right? So that can happen when you're hungover too. If you're like hungover and your heart rate goes up. So that's not a good day, especially with tequila, because tequila, like you sweat it out and then you're just like smelling your bad decisions, your poor life choices the entire next day. It's like a self-punishment. Okay, so next, let's talk about positive feedback. And positive feedback is the opposite of negative feedback. Positive feedback, when it's going, it's not homeostatic because positive feedback, again, you have to dump your normal associations with the word positive because it's not necessarily good. As a matter of fact, most of the time it's not good. And it's also not necessarily up. So with negative feedback, if it got hot, you turn on the air conditioner. With positive feedback, if it gets hot, you turn on the heater and you add to whatever direction something was going. So the description is when the deviation from normal occurs, the response is to make the deviation larger, okay, to continue going that direction. So what you would do is, I'll give you a couple of examples. So you'd sort of add to whatever was going on. So if this was blood pressure, and this was time, and I had damage to an artery, okay? If you damage an artery, then what's going to start happening to your blood pressure? It's going to drop. And then your heart will go, I know how to help. And what will it do? It will pump harder. Unfortunately, that is not helpful, right? And it would tend to make you lose more blood, right? And so as long as that system was going on, you would be in a positive feedback loop, because before you got the hole, everything was totally cool with your blood pressure. Then you got a hole in your artery and it went down, and then your heart tried to help, and then it continued to go down. With positive feedback situations, you generally either have to have an intervention, right? Somebody plug the freaking hole, right? Or sometimes you just die. And it really depends on how young and healthy you are and what particular thing is going on. But here's another example. Have you ever gotten a fever so bad that you started to shiver? Yeah. So what's happening there is during that particular time in which the fever is that bad, you starting to shiver, is actually you're in the positive feedback part of the loop. So your temperature went up. Shivering is a way to increase your body temperature. It is going to add to that. Now sometimes it's okay because your body's trying to increase the temperature such that the pathogens will die off, which is okay if you're like in your 20s, right? Maybe even in your 30s. But if you get to that stage in which you go up to like 103 and it's a 3-year-old or an 85-year-old, then remember that your homeostatic control mechanisms are not as good at either ends of your life as at grabbing back hold of it. If I were in my 20s, because I was always freaking broke, I probably would have just ridden it out. It's fine, I just got it. I'm just going to ride this out. I'm pretty sure I'm not going to die. And I was right? Because I'm still here. But now I'm no spring chicken anymore. I'm going to go take an ibuprofen. I also dislike being uncomfortable now. I'm like, oh, God, that's terrible. Your homeostatic control mechanisms have an age in which they're really, really sensitive, and then at either ends of your life, you know that they're not. So if you're a parent, if you ever had a kid that had a temperature that went up to 103 or 104, you are immediately going to try some intervention. You're going to throw them in a cold bathtub, you're going to get them cold blankets, you're going to give them some kind of intervention with Motrin or whatever, and the same thing with very elderly people. So positive feedback situations, they don't have to go one direction or the other. It's just that whatever your body responds is actually adding to the direction that it's going. Now, are there ever any normal or healthy positive feedback situations? And there are, because sometimes you really want to get something done once you start it. A great example is childbirth. So, you don't want to fart around with that. Nobody I've ever talked to loved that enough that they wanted to do it for like a week straight. So what happens with childbirth is that it's going to start a little positive feedback loop. And let's say the baby gets to decide when they're baked and not the doctor who has scheduled a vacation. But when the baby is full term and things are working perfectly, what's going to happen is the baby is going to start to release oxytocin, which will cause uterine contraction. But the uterine contraction will cause the release of more oxytocin, which will cause more frequent and stronger uterine contraction, which will cause the release of more oxytocin. Does that make sense? And so what you continue to do is you continue to have contractions, increase in frequency and strength, and oxytocin level go up and up until you accomplish the event that you were trying to accomplish, which is parturition or birth, right? And so you can see that with positive feedback, if once you start something, you want to finish it, that's a decent way to do it, right, to add to it. Another example is blood clotting. If I damage a vessel, let's say it's not an artery. Artery is really difficult to clot before you die. But let's say I damage a vein. And it's a small damage on a vein. What happens is the damage will attract platelets, which will start clotting. But the clotting itself will attract more platelets, which will amplify clotting, right? And so you continue to add to this until you accomplish the event you were trying to accomplish, which was blocking or plugging the hole, right? And there are a couple of other examples of normal or healthy positive feedback. But do you agree that even if they're normal and healthy, during that particular part, you are not in homeostasis, right? When you're amplifying I mean, you may be eventually having a goal, but during that part, you're not in homeostasis, right? Okay, so birth, blood clotting, action potentials, which is a way of getting really fast nervous system transmission. We'll talk about that a lot. That's also a positive feedback situation. And estrogen secretion is as well. These are sometimes called a positive feedback cascade or a positive feedback amplification or loop. And most of them are disease situations, and there are a few normal situations. Okay, so let's go back and talk about putting all this terminology together with things that you've done before. So why do we spend this time talking about homeostasis when I know it's a topic that you've had before? Because it is the unifying theme of physiology. It is the best prediction for what's going to happen. So generally, if there's a disturbance in a variable, your body is going to try to restore it to homeostasis. And then the rest of the semester is going to be a lot of examples of mechanisms by which you do that. Like, how do you restore it to homeostasis? But knowing that if your blood pressure goes down, your predictor is that your body is going to do damn near anything necessary to bring it back up, including but not limited to vasoconstriction, increasing the heart rate, water retention, right? All to bring your blood pressure back up. That gives you a strong basis in prediction for physiology. So that's why we spend some time on it. So as I mentioned, the primary fluid that you are monitoring most frequently is the extracellular fluid, and you are monitoring what kinds of variables? Just damn near all of them. Almost every variable that you never even thought of. Your potassium concentration, your sodium concentration, your oxygen concentration, your pH, your pressure, your water concentration, they are all right now being monitored by their own little reflex arcs, primarily in the extracellular fluid. And you never get to stop the assessment. And if you did, you probably wouldn't be alive for very long. So that's why it's incredibly expensive. So your body's internal environment, because of all these reflex arcs and negative feedback going on, it remains relatively constant. But we know that I mean something different by constant than other people mean when they say constant, right? So if I say my body temperature is relatively constant, it's not actually constant. Is it going to stay at 98.6 for any long period of time? No, it's going to maintain predictable variability, right? It's going to be predictable over a long period of time. I can really guess at what the range is going to be if I get enough data points. So now let's talk about what is useful for a clinician or for someone going into human health to know and assess. So obviously in my hypothalamus somewhere, there is an ideal set point that is my ideal temperature. But we know that my hypothalamus accepts a range around that, right? Okay, and my hypothalamus doesn't speak math, so my hypothalamus can never tell me what the set point is. The best way that I can get an idea of the set point is by averaging the mean from a long period of data points, right? So my mean body temperature is my best indication of what my set point might be, right? And by the way, that can change as well. But if you are actually going to go into anything related to human health, which one is more reasonable or more useful information to know? The mean, the set point, or the range for a variable? The range. Unfortunately, that of course means that you need to memorize 2 numbers instead of 1 number. But you don't want to be the person who, like, oh, doctor, I've got 120 over 80 memorized, and they're 125 over 82. No, you don't want to do that. You want to know the acceptable range. And you won't know it for everything. But if you go into treating diabetics, I'm pretty damn sure you'll know it for glucose, right? And if you are the nurse who does the initial intake, you will know it for blood pressure, right? So the body does not really maintain a set point. It maintains a steady state, which is a wiggling variability around the set point. The most useful information to memorize is the range. So now let's just talk about variability for a little bit. So what do we expect for variability? Well, you've been a human, you know that variability in any variable over time is normal, right? It doesn't stay at one point over time. But you know that it's also relatively predictable. But you also know that variability between individuals is normal as well, especially if you have a significant other. If you've ever lived with another person, let's talk about temperature, right? Okay, you're gonna have thermostat wars. I swear they're probably third after sex and money for things that like piss people off about each other. So my ideal temperature is probably like 2 degrees lower than my husband's, and so he's always turning the thermostat back up, and I turn it back down. He turns it back up, and I turn it back down, and then I just blame it on the kids when he asks. I'm like, I don't know who did it. So variability between individuals is also normal. But do you think that the variability is going to be dramatically different? Or if I had a range of healthy human body temperatures, I could predict that my husband was going to be within that range. He might be here, right? And I was going to be within that range, and I might be here, right? So there is a healthy and there is an unhealthy, and most of us are going to fall somewhere along it. But the mean for an individual, my time averaged mean is relatively constant, with the exception of the fact that I can have seasonal variations, and I'll talk about that in just a minute. So you already know this. Which is more likely to indicate disease? Variability from the set point, variability from the mean, or variability from the range? Which one? Range, but only if what? I have to meet a couple of criteria that tells me that disease is a possibility. It has to be consistent, and it has to stay out for a long time, right? It has to like stay out too high for a long time, and then you can diagnose as hypertension, right? Okay, so let's talk about body processes related to homeostasis, and you guys are going to be doing some of this in lab this week. You are going to be measuring some of your own variables over time, right? And some of those rhythms that you will see vary over a 24 or 25-hour cycle. And those things, those variables that vary very dependably over a 24 or 25-hour cycle are called circadian rhythms. Circadia means around a day. Okay, so in order to have something that varies over a cycle, I need a pacemaker to know when the cycle begins and ends. And the part of the brain that is most involved in being the pacemaker is the hypothalamus. But the hypothalamus has to take input from the external environment to figure out when to reset for the day. And that input mostly comes from temperature variations and light variations. So that helps you set your 24-hour clock with the external environment's 24-hour clock. Before we go any further, what about a person who has no external cues, like someone who was underground in isolation for long periods of time? Would they still be on a 24 or 25-hour cycle? They are, but it's completely disconnected from the external environment. Your body still will find one, but it's not connected to the external environment. So we're still set up to have circadian rhythms. Okay, so the hypothalamus is probably the pacemaker. And one of the things that it does that's really important is tells you when to go to bed, which is kind of your reset. So the hypothalamus tells the pineal gland when to release melatonin. But then a whole bunch of other things are 24, 25-hour cycle. A bunch of your hormones like insulin and glucagon and cortisol and all of those. Your activity and metabolism patterns vary over a 25-hour cycle. So here are some things. This is a typical person, and this might not be you. This is a typical person in looking at your circadian rhythms, and because of your hormonal and ion compositions that vary over the course of a day, you have some dependable stuff that happens. So if we start at midnight arbitrarily, I don't know why the hell they didn't put midnight up there. It makes me mad. But so I know it's a 24, but I just wanted it to be on the top. Okay, so midnight is here. Your deepest sleep with this person's particular 24, 25-hour cycle is at about 2 a.m. And then the lowest body temperature is about 4:30, a lot of time to cool down the body. This person probably went to sleep right between here and here. Okay, so 4:30 is when you have your lowest body temperature, your lowest metabolism. And then if you're going to get up about 7, you're going to have an increase in blood pressure about 6:45, assuming that you are not waking up to an alarm and you're using anticipatory homeostasis. So you get a big bump in your metabolism, and it makes it very hard to stay asleep. And then your melatonin secretion is going to stop. Now you're done. I'm officially awake. My melatonin is over. And then you're going to poop. Have you ever wondered why you don't poop in the middle of the night? It's because, among other things, the hormones that are released to make you sleepy make you not have to poop, which is really convenient, because wouldn't that suck? So this happens, bowel movement is likely, especially if you're drinking some coffee. That's definitely going to happen right about there, okay? And then your highest level of alertness is about 10 a.m., which is great, because that's when I teach this class, right? If you talk to me at 7 p.m., I am dumb as a stick, okay? 4:30 a.m., ain't nothing going on upstairs. Okay, and then noon hits. Your best coordination for this person is about 2:30. Fastest reaction time is right after that. This is when you need to work out, like 5 o'clock when every other Yahoo goes to the gym. Super annoying time to go to the gym. Highest blood pressure and body temperature is after that, and then melatonin secretion starts again. And this is all regulated by circadian rhythms, primarily regulated by a bunch of hormonal release at different times during the day. So you are going to start to assess some things this week. What are you measuring? You're measuring body temperature, reaction time, and pulse rate, right? I wish I could have you guys measure cortisol, but they're all weird about you measuring like body fluids. I figure if it's yours, you should be able to measure it. I'm working on it. I also want you to be able to measure some stuff in your pee, but the college keeps saying, no, no. I'm like, it's their pee. It's not like they haven't peed on themselves before. It's work. It's fine. Okay, so also circadian rhythms are involved in regulating sleep-wake cycles, regulating your body temperature, your hormone concentrations, and all of this, if works really regularly, will get you anticipatory homeostasis or feed-forward mechanisms. Okay, so now let's talk about a couple of other things that are related to this, which you're going to run into all semester long. And this one I never actually ran into until I started took physiology and then started teaching physiology. And it's pretty damn fascinating. Okay, so we're going to try to regulate a variable. This time we're going to try to regulate one we haven't talked about before. And so I've got a male and males have an acceptable range of testosterone in an adult male, normal range, right? And females have testosterone too, but their range is much lower. So I have a male who has consistently low levels of testosterone. And that will impact not just sex drive, but also metabolism and mental acuity and drive. Over a long period of time, not days, not weeks, months or years, he's unable to regulate his testosterone back up into normal levels. He has consistently low levels of testosterone. So what happens eventually is your body will go to plan B. If I can't effectively regulate my testosterone concentration, I will go to plan B, which is to regulate my body's response to testosterone. Testosterone interacts with receptors on its target cells. So what do you think would be a reasonable plan B in response to sustained low levels of testosterone? I can either increase or decrease the number and sensitivity of my testosterone receptors. Increase, exactly. That is called upregulation. It is a second-tier response to a long-term, low level of a variable that I have failed in regulating. So I will upregulate my testosterone receptors, and then I'll get some relief from the symptoms without actually upping the level. Does that make sense? Okay. So that's called upregulation. Downregulation, there's an even more pertinent example to downregulation. Okay, so downregulation will be the body's response when I cannot regulate a variable that's been too high for a very long period of time. So this is a story that will probably be familiar to you, and you guys can tell me what disorder I'm talking about when I get done talking about it. Okay, so I'm from the South. Notoriously terrible eating habits in the South, right? And so, and also the food's amazing and will make you super fat. If you ever want to feel really good about yourself, just go to the airport in Atlanta. You're like, oh my God, I'm so hot. This is amazing. It's true. It's like all you have to do is be in a room full of fatter, older people, and you're like, oh, I'm totally fine. I've got a person who typically drinks between 3 and 6 Dr. Peppers a day. Okay, it's really, really common in the South, super common. So between 3 and 6 Dr. Peppers a day. And so what's going to happen is I'm not going to do that for a week. I'm going to do it for a decade, maybe 2 decades, right? And that's just going to be the habit that I have. In addition to being heavy, I want to talk about what's happening with blood sugar and insulin. So what's going to happen consistently with your blood sugar is it's going to spike after you drink a Dr. Pepper, and then your insulin's going to spike, right? And your insulin's going to try to bring down your blood sugar, but then you're going to drink another Dr. Pepper. So your sugar's going to spike and your insulin's going to spike, right? And this is going to happen over a very long period of time. And after that happens over a very long period of time, then my insulin level is consistently very, very high and failing miserably to regulate my blood sugar. And so what is going to happen over time is that this person is eventually going to change the number and sensitivity of the insulin receptors. And what do you think is going to happen? Am I going to increase or decrease the number and sensitivity of my insulin receptors? Decrease. That is called downregulation. And when I downregulate my insulin receptors, the thing happens. What is that called, by the way, when that happens over a long period of time? Type 2 diabetes. The problem with that is that means that you are not going to respond normally to normal levels of insulin. So anytime you're not drinking 6 Dr. Peppers, when you are, for instance, sleeping, normal levels of insulin will not get your cells to uptake sugar. And so your cells are going to start having booms and crashes of sugars, which tends to be very damaging, especially to tissues that are non-regenerative, like the nervous system and cardiac muscle. So this is the biggest increase in like a preventable disease that's happened in the United States in the last 20 years. And it used to be that we called it adult onset diabetes for decades because people didn't used to get it until their 30s, at the earliest. And now we have kids that are as young as 7 years old getting type 2 diabetes. It's a completely preventable disorder. But if you go in the South, go into Walmart, somebody's going to have Dr. Pepper in a baby bottle. It's going to start then. And it's just, a lot of it's just lack of education. You don't really know how to describe what's going to happen. So that is an example of downregulation. So all semester long, we will see that if you fail at plan A, then very often you will try plan B. Sometimes plan B fails too. Like with a type 2 diabetic who doesn't regulate after type 2, they can end up with insulin-dependent, insulin-resistant diabetes. So they have to inject, but they don't get to inject normal levels of insulin. They have to inject outrageous levels of insulin. So we'll talk about diabetes a ton this semester. Okay, so that's upregulation and downregulation. The next things, let's just talk about aging very, very quickly. What is happening with aging and how is it related to this whole negative feedback and stuff? Aging is, as you start to get older, what happens is your homeostatic control mechanisms are just not quite as sensitive and as fast to respond. So instead of staying out for a short period of time, you stay out for a long period of time. And when that occurs, you're more likely to accumulate damages. So little small insults because you're not catching your homeostasis. And they're cumulative, right? And so aging is sort of this progressive, small failures of homeostasis that allows you to accumulate damage into your system. So it's directly related to this stuff. And then the other thing is an adaptation or acclimatization. So adaptation or acclimatization has to do with the fact that you can reset your set points for variables based on changing external stimuli. So first example is this. Okay, so every year when it starts to get cool in the fall, right, you're freaking freezing when it's like 70 outside, right? And you need a hoodie and you need some socks, right? You start to get really, really cold as soon as it gets a little bit cool outside. But as soon as it is consistently cool and you give it about 2 weeks, then you're no longer cold at 70 degrees and it feels amazing. The same thing happens on the other end. It starts to get warm every spring and you get in your car and you're like, oh God, why do I live here? It's so hot. And then you give yourself 2 weeks and then you're actually acclimated to it. So what happens is, just like your thermostat in your house, you can change your thermostat just a little bit so that it's closer to the external environment, but was still within an acceptable range. But you don't do it instantly. Like you don't change your thermostat in your house down the first time it gets cool, right? Because it's inefficient to do that. You have to change it right back up. So what your body waits for is if it has a consistently larger error message in the same direction over a long period of time, then it can change your set point just a little bit to be more efficient. So as it starts to get cooler, then if my body was set at 98.6, it can go, okay, well this will be more efficient and she'll still be comfortable if I set it down to 97.6, right? And then she won't be cold all the time. That makes sense? And the same thing happens on the other end. So it happens every year, but it doesn't happen the first time it gets cool because you really need for it to be a consistent error message, right? Okay, and then the other example that a lot of you guys probably have experienced is, so I'm from Texas, which is really low elevation. It's really low elevation, which means there's a lot of oxygen in the air there compared to here. Anybody else move from low elevation to Utah? Okay, so this is a really freaking rough first 2 weeks. First of all, I moved to Provo without knowing what the hell I was doing. I couldn't figure out why I couldn't make a friend. My neighbors didn't want the wine I brought over. I was shacking up with my boyfriend. I was like, come on over. Nothing. No friends whatsoever. And on top of that, I couldn't walk up the freaking stairs. I'm like, oh my God, what is I couldn't breathe. And I was like in better shape then too. I was like, oh, this is terrible. It's the worst place I've ever been. And I cried, and then all of a sudden, like, my body is like, you're staying? And I'm like, oh, well, yeah, I got a job, I'm totally staying. It's like, all right, well, don't tell me I didn't tell you. And so what happened is my acceptable number of red blood cells that was adequate for carrying really high oxygen content air in Texas was much lower than it was here in Utah. And so after I was here for a little while and the error message was consistent, right? You're still low oxygen, you're still low oxygen, you're still low oxygen. Then what happened is my body said, okay, you need to make more red blood cells, and released a hormone called erythropoietin from the kidneys, which tells my bone marrow it needs to make more red blood cells, and readjusts my set point for acceptable red blood cell content. Does that make sense? Okay, and then I was okay. I still lived in Provo though, so it was a rough first year. And then I moved up to the avenues with all the rest of the hippie liberals, and that's fine. I was like, oh, we're gonna be fine. Go ahead.
How long does that take to, like, let's say you go back to Texas? How long does it take then for you to lose all of that?
Well, it's very different with different variables, but usually with resetting your blood, it's a minimum of 2 weeks. And of course, they use that for competitive elite athletes, right? Because if you want to increase your oxygen carrying capacity and you're in a cardiovascular sport like cycling or something, you go train in Park City, right? Regardless of whether you're competing in Louisiana. But it ends up being no advantage at all because all of them do it, right? All of them, right? So it's at least a couple of weeks and usually months. However, it takes a little longer to reset back down because there's no disadvantage to having high levels of red blood cells. So what happens is as soon as you start like lysing them as they go through your liver and your spleen, you're just like, it's fine, just don't replace them because you're still like not getting an error message. So it takes a little longer to reset back down. When you came back from where?
I came back from back east. I came back and did a long run, and I felt it, but it was.
You felt it here?
It was really in my head, up in Park City.
Oh, up in Park City. And how you were back east where?
2 weeks, sea level.
Oh, at sea level. Oh. Oh, so it was harder when you came back? It was harder to run?
I felt like I could tell it.
Oh. Well, it might have been. I mean, well, it could have been in your head too, but I don't know. People are different about their capacity for doing that. Okay, so we're going to stop there for today, and we'll do chemical messengers and homeostasis next time. Remember, my objectives for you for next time are clickers in hand. That's objective number 1. Register it as objective number 2. Okay? And we're going to play around with the clickers with something non-graded when I see you guys next time.
So, if I fail to register at 3:30 today, there's no post today.
Oh yeah. Well, I don't do anything
You can't
after
do
today.
anything
No,
at the backside.
but somebody will drop.
Okay.
Just so you know, the most persistent student will get in. You just have to continue looking.
And is it going to be okay? Like, can I, like make up the assignments that are online? for registered students only?
I don't have any assignments online for registered
Like the
students.
clickers and stuff?
What you can do, if you have a clicker, if you go ahead and decide to purchase one, I will keep your grades
Okay.
for when you get enrolled.
Cool.
Yeah?
Great.
Okay. Hi.
Hey, do you upload the PowerPoint or I guess your